Okay, have you ever really thought about this? Why can a diamond survive the insane heat of a volcano, but the graphite in a pencil, which is the exact same stuff, crumbles with just a little bit of pressure? I mean, they're both just pure carbon. So what gives? Well, the answer isn't what they're made of, but how they're built. Today, we are diving deep into the invisible architecture that makes a diamond the undisputed king of materials. So what is the secret? What makes this one substance so tough it's practically indestructible? How can a diamond handle temperatures that would turn solid steel into a molten puddle? It's not magic, not by a long shot. It's chemistry. And it's a secret that's been hiding in plain sight deep inside the atom itself.
All right, first up, the indestructible diamond. We really need to look past all that sparkle and just appreciate this thing for what it is, which is a masterpiece of molecular engineering.
Yeah, for a chemist, the shine is almost secondary. The real marvel is its sheer indestructibility. You know, most materials have a melting point, right? A temperature where they just give up and turn into liquid. Diamonds, on the other hand, they just don't. They can take an absolutely incredible amount of punishment. And that amazing resilience is our very first clue. So, where do we even start looking for answers? Well, let's zoom all the way into our primary suspect, the single element that builds a diamond from the ground up. Let's talk about the carbon atom. And we are talking 100% pure carbon here. A diamond is what we call an allotrope of carbon. It's just a fancy word for a specific physical form it can take. The graphite in your pencil? That's another allotrope. The only, and I mean the only, difference between the hardest substance we know and one of the softest is how those identical carbon atoms are arranged. You see, the carbon atom has a secret weapon. It's got 4 electrons in its outer shell, and they're all just itching to form bonds. Through this unique atomic shuffle, chemists call it sp3 hybridization, it arranges these electrons to create 4 perfectly identical and totally symmetrical bonding points. This perfect symmetry is exactly what makes carbon the ultimate building block. And these 4 bonding points aren't flat. No, they point outwards to the corners of a 3D shape called a tetrahedron. Just picture a little pyramid with a triangular base. This geometric shape, this is the fundamental blueprint for the entire diamond structure. So we've got the blueprint. Now let's look at the mortar that holds this whole thing together. This is the atomic superglue, the incredible force that locks these carbon atoms into their unshakable fortress. And here it is, the essence of its strength. Every single carbon atom uses those 4 tetrahedral points to link up perfectly with 4 others, and the connections they form are called covalent bonds, literally one of the strongest chemical bonds in all of nature. This is our atomic superglue in action. This fortress is built atom by atom. You start with 1, it bonds to 4 others in that perfect tetrahedral shape. Then, each of those atoms bonds to 4 more, and so on and so on. The pattern just repeats, extending outwards in all 3 dimensions, creating this perfectly rigid, completely interconnected lattice. And when we zoom out, we can finally see the grand design, a true fortress of bonds. And believe me, understanding this design is the absolute key to understanding why a diamond is so incredibly strong. The official name for this whole setup is a giant covalent structure. And that word, giant, is so important here. It means there isn't a single weak link in the chain. The network of these powerful bonds is continuous, running through the entire crystal without a single break. Okay, get ready for the aha moment. Let's compare a diamond to something like, say, ice. Ice is what we call a molecular solid. It's made of individual H2O molecules that are just kind of held together by relatively weak forces. So when you heat ice, you only need a little bit of energy to break those weak links, and boom, it melts. But in a diamond, there are no separate molecules to break apart. It's all one continuous bonded structure. This quote right here really drives the point home. The entire diamond is essentially one single giant molecule. Just think about that for a second. An entire diamond, no matter how big it is, acts as one single, unified, massive molecule. To affect it, you can't just nudge some molecules apart. You have to wage war on the very atoms themselves. Which brings us right to our final section, breaking the unbreakable. Let's put some hard numbers to this incredible, incredible strength.
So the big question is, how much heat, how much raw energy does it actually take to finally overcome this atomic fortress, to break millions upon millions of those powerful covalent bonds all at the exact same time? The answer is just staggering, 3,550 degrees Celsius. Now, to put that into perspective for you, steel turns to liquid at around 1,500 degrees. You need more than double that heat to even begin to bother a diamond. That is the power of that covalent bond network. And in fact, it gets even crazier. At this extreme temperature, a diamond doesn't even bother melting. The bonds absorb so much energy that the atoms skip the liquid phase entirely and just break free, turning directly into a gas. It's a process called sublimation. Wild. So, what's our final verdict in the case of the indestructible diamond? Well, when you get right down to it, it's all in the geometry. At the end of the day, a diamond's toughness isn't some mystical, magical property. It is the direct, logical, and inevitable result of its perfect tetrahedral architecture, locked rigidly in place by the immense strength of those covalent bonds. It's simply a masterpiece of atomic efficiency. And that kind of leaves us with a final thought, doesn't it? If the simple arrangement of carbon atoms can create something as extraordinary as a diamond, what other incredible secrets about the nature of our world are just waiting for us to find them, locked away in the invisible architecture of atomic geometry?